So I'd like to thank the organizers for inviting me to speak today. It's the first time I've ever been giving a talk where people had to be scanned in like a concert venue. That's pretty cool. So I'm going to talk today about correctly modeling networks. So I'm trying to be a little bit provocative with the title. This is joint work with Aksoy, who's a graduate student at UC San Diego and spent a summer at Sandia. Ali Pinar, who's sitting right there, and I'll point to now and then to blame for things. Todd Plantenga is a former Sandian now at the place called FireEye, and Commander Seshadhri, who we know as Sesh Commander, who's a former Sandian now at UC Santa Cruz. So our goal in correctly modeling networks, so I come from a mathematical background, and so we really want to understand how things work. And the way we convince ourselves that we know how something works is that we can model it correctly. And when our models are wrong, that's also interesting to us, because we learn something about what the shortcomings of the model are, and then what it is that we learn more about what we're trying to study. So I'm going to tell you what I think about some of the models out there and what their shortcomings are, and I'm glad that they're wrong, because it teaches us something. And I'll tell you about some ideas for maybe doing a better job, but then I'll end telling you all the things that we're still pretty poor at doing, and maybe opportunities for more understanding through better model development. So we'll start off with the easiest thing. So degree distributions. On the left, we have a picture. It's in log-log scale. And it looks at the number of nodes of each degree. And there's many nodes of low degree and few nodes of high degree. And that's what we often see in many types of networks, especially social networks. You can look at frequency of words and all sorts of things. So let's look at some of the classic models. So the classic model is Erdös-Rényi. Every probability of an edge between two vertices is just a constant, like 0.2. And you end up with what looks like a Poisson distribution of the edges. And so that looks like a hump, sort of like a bell curve. And that picture that we see here does not look like a hump. So that would be wrong. So that's well known to be a bad model of realistic graphs. Then there's stochastic block model, still very popular, especially in community detection. And every node is assigned to some block. There might be 4 blocks, or even just 2 blocks, or even 100 blocks. And then the probability of an edge between 2 nodes depends on what blocks they're in, and it's constant for any pair of blocks. And this is just a mixture of Poisson distributions. Oh, still not quite looking like the distribution on the left. Preferential attachment was a big step forward. This idea of this is you have a node that's built up sequentially. Every time a node joins, it gets to make so many connections, and it preferentially chooses the nodes that already have more links. So it's the rich get richer. And so this is nice because it gives a parallel distribution that looks a little more like what we see on the left. So it's a little closer, but it's still sort of a story-driven model, driven in part because the previous models didn't do a good job. But it's very hard to match that to real data, because there's really only one thing you can tweak, which is the number of nodes that each new node connects to when it joins a graph. So we are interested in really matching things on a quantitative level rather than qualitative. So being parallel is good, but how do you get a preferential attachment graph to match what you see in real data? It's pretty hard if you've ever tried it. And in fact, the parallel might not be correct. There's been a couple of papers by Bai and others and Sal and others that have sort of made this claim. It's, in general, hard to say if anything is parallel in any case. And actually, if you just take 2 degree distributions and you want to compare them, how do you do that? And so I think the answer is maybe still unknown, but in a paper on understanding streaming degree distributions, Simpson, Seshadhri, and McGregor, I think at least one of these people is here today, come up with a method for comparing 2 degree distributions so that they can say if their streaming method did a good job. So that was actually the hardest part of the paper, was to prove that their streaming method was working. So, but today I'm not going to be that complicated. I'm just going to do the eyeball norm to convince you the degree distributions are right. So degree distribution is one thing that's seemingly hard to match, and we'll talk more about that. And then the other one is what's called clustering coefficient. So particularly for social graphs, this is very interesting because it gives us some idea about social cohesiveness. And so there's the first basic quantity is something called global clustering coefficient, which is the number of closed wedges divided by the number of wedges. So a wedge is a two-path, and it's closed if that third edge exists. We have an example on the left. And so that's just 3 times the number of triangles over the total number of wedges or two-paths in the graph. So it gives you some sense of how dense are the triangles in your graph. And what we see is that many real graphs have many more triangles than you would expect for a random graph with the same degree distribution. And so this is maybe interesting. So it tells us something is wrong with a model that just matches degree distribution. And so there's Sala, who also said something about power laws, also showed that most generative models fail to match the clustering coefficient of large-scale graphs. The other interesting thing is the clustering coefficient varies by degree. So you can define a clustering coefficient for a degree, which we show up above. So it's the number of closed wedges that are centered at a node of degree d. So if 1 is the center in that graph on the left, and then you check and see if it's closed. You can look at the average number. And on the bottom, we have a picture, which you might be able to see if you sort of look up on your tippy toes, which shows that this is a co-authorship graph here. Low degree nodes have higher clustering coefficient than high degree nodes for the most part. And this means if this is a co-authorship, so if 2 authors write a paper together, 2 people write a paper with a third author, then they are likely to have written a paper with each other as well. And as the number of authors grow, the chance that the pairs of authors that are connected to a similar author have also written a paper together gets lower, which sort of makes some intuitive sense. And then this network is funny because it has this big bump up around sort of degree 30, and that's some paper that had a lot of authors that sort of makes the number artificially inflated. And so this is interesting. It varies by degree. And if we're trying to look at how to reproduce these numbers, having more than just a lump sum number makes it a little more interesting. So one of the popular models, and we've heard it mentioned earlier today, is stochastic Kronecker graph, sometimes called SKG. It's also originally known as RMAT, recursive matrix. So this comes from an SDM paper in 2004, and there's been several other papers since then. This model has one great feature, which is that edge generation is really, really cheap. And I work at a national lab where we work on almost exclusively on really large problems, so we care a lot about scalability. And it costs only log n, where n is the number of nodes, to generate each edge. So that's great. Moreover, the generation of this method, the stochastic Kronecker graphs, is embarrassingly parallel. So we love that. That means I can generate every edge separately, and so I can have a lot of processes going. It was selected as a benchmark for something called Graph 500, which is a way of testing computers for maybe like purchased by the government, or you just want to see how well they do on graph problems. You can use this to generate graphs that you'll run algorithms on. It has only 5 inputs. People don't like a lot of inputs, so this only has 5. Number of nodes should be a power of 2. Number of edges, and a 2x2 stochastic matrix by which all the entries add up to 1. So you really only have 3 independent entries there. So 5 parameters, so that's good. It's somewhat slow to fit to real-world data, but a bigger problem is that it doesn't actually produce realistic degree distributions. So over on the right-hand side, the blue is what stochastic Kronecker graph gives as a degree distribution for the parameters that the Graph 500 uses, and it has this oscillation, which we don't really see in real-world data. We did some work in an ICDM and JCM paper that tried to fix it a little bit. So if you add a little bit of fix, you get the green curve. You add a little bit more fix, you get the red curve. And so you can maybe sort of fix it, but there's a lot of other problems with this model, including that it's slow to fit, including also that it doesn't produce many triangles, so it doesn't capture that social cohesion. So that's what I'll say about that. What I like, if you want to just get degree distribution, is sort of an old-fashioned model that has a couple different names. Chung-Lu is what I usually call it. It's also known in physics as the configuration model. The basic idea is the chance of an edge between 2 nodes is proportional to the desired degree of those 2 nodes. So if you want to have a Chung-Lu graph, what you give it is the degree of every node, or you can give it a degree distribution, and it can pull that from there. There are different ways to implement it. So in Chung-Lu, they were mostly doing theoretical analysis of these graphs, and they basically said you flip a coin for every edge. So I mean, you have to do n-squared coin flips. That's a little bit slow. You can do what I call stub matching. So if I have a node of degree 3, it has 3 stubs, and a node of degree 4 has 4 stubs, and all the nodes have these stubs pointing out. and then they somehow get matched up by a random matching. So that's low complexity order n, but it's sort of a little bit sequential. And the last is what we call sort of fast CL, and it's 2 weighted coin flips per edge. So I just pick a node out of a bag proportional to its desired degree. So a node of degree 100 is 100 times more likely to be picked than a node of degree 1. And so I'll pick 2 of those nodes for each edge, and then I can generate all of those in parallel. With both the stub matching and this fast version, you will get repeat edges, you will get self edges, but they're actually very few, especially for large-scale graphs. For small-scale graphs, this could cause a problem. You go back to the coin flip, but for large-scale ones, you get very few of these problems. This still has the problem that it doesn't produce many triangles, and I'll show that on the next slide. But on the degree distribution, it gives a nice, happy match. And so if that's what you're looking for, then your problem is solved, and you can sort of go to sleep for the rest of the talk. You can correctly model this. But what if you want clustering coefficients? So the graph on the left shows what Chung-Lu does in green, which is all along the bottom. Those are the triangles it's producing, almost none. But the real graph, a citation graph in this case, has a lot of triangles. And so what's the problem here? With large-scale graphs, if a node connects to 2 other nodes, there's really no reason for them to connect to each other. And when it's sparse, which these real-world graphs are, then you don't see many connections. So what does this mean? So we spent in my sort of research collaboration a lot of time arguing about how do you have graphs that have this power law degree distribution, but also have some non-trivial clustering coefficient. How can that be? I mean, we actually proved a theorem that a Chung-Lu graph, so the degrees are distributed according to this probability, with high clustering coefficient, must have a non-trivial Erdős-Rényi subgraph. So a dense subgraph is inside this large sparse graph. And that's sort of counterintuitive, because we said at the beginning, Erdős-Rényi is the worst way to model graphs. You're not supposed to do it. Goodbye, Erdős-Rényi. But what we're saying is that there's something in there, this dense subgraph structure, that actually does have meaning. And so that's sort of interesting. This is where I'm happy as a mathematician, because there's some fundamental understanding that's taking place that's guiding us. And so based on this theorem, we decided that we'll create a new model, because that's what you do in this business, that has now what we call affinity blocks. And we call them that so you don't confuse them with clusters or anything else. These are dense blocks inside the larger graph. And they generate many triangles. So it's very hard to see. I think there's a graph on the right that's just an Erdős-Rényi graph on 20 nodes, the probability of connection of 0.3. And you can just look at it, and there's just lots of triangles in there. You don't have to have a very high connectivity to get a lot of triangles. And in fact, you can even work out, if I want this many triangles in my graph, what should my probability of an edge be? And it's sort of this cube root of the clustering coefficient. There's some stuff we like to make everything very parallel and everything running independently. This causes some problems if we're generating a graph and we want to make sure we get so many independent edges in our little dense subgraphs. We have to think hard about how many draws we have to do in a completely random and independent fashion. And this turns out to be a coupon collector problem. I'm not going to go into the details of all that today. But the basic idea is we need these dense subblocks. So we want to sort of take this Chung-Lu, which is great for degree distribution, and take these little blocks, which are great for triangles, and see if we can combine them. And so the way we do this is in this model that has different names. It's BTER. So we sometimes call it the BTER model. That was sort of a cute play on words that we thought was so funny when we came up with it. But now I just sort of call it the BTER model. One person called it the BTER model. That's pretty terrible, but so don't call it that. But there's sort of 3 basic steps. One is to create the affinity blocks. And so we make terrible assumptions on this. And so you should all be critical of this. I'm critical of it. But they sort of work for practical purposes. So we have non-overlapping affinity blocks. And the basic idea is we would like all the nodes in an affinity block to have the same degree. An ideal situation is we have d plus 1 nodes of degree d. If they're all connected to each other, we'd have a clique, and the clustering coefficient would be 1. So that's why we like that. We can get all the way up to a clustering coefficient of 1. And then we have 2 pieces. Phase 1, we add a bunch of links inside these affinity blocks. And those are creating our triangles. And then we basically have some of the degree that goes into those. That's sort of the d hat. So we split the degree for each node into the part that goes to the affinity block, the d hat, and the left is sort of excess degree, and that we throw into a Chung-Lu model, and we finish up by connecting the rest of the edges by a Chung-Lu model. So a really high degree node might be in a small affinity block, say, but he then can have a bunch of excess degree that connects to other nodes with excess degree. So we still get the degree distribution, but we also get the triangles. And then we did a lot of fanciness in our work to try and make sure that these edges can be generated independently, so you don't have to run phase 1 and then phase 2. We use a lot of statistics and just work with expectations here. So what's the expected amount of the degree that will contribute to the phase 1? And it can even be a non-round number. 2.7 of the degree will go to that. And then what's the rest that goes to excess degree? So we're running everything in expectation, and the great thing about large-scale graphs is it all works out in expectation. So things sort of come out, and so we can run everything in parallel. So I want to stress that the affinity blocks are really small. So what are we picturing here? It's an adjacency matrix of a parallel graph. And so we have just sort of lots of connections, little dots, and then you see this little sort of diagonal line on the lower right side. Those little beasts are the affinity blocks. So we have lots of them, and they're tiny. So very different than what you might see in a stochastic block model, where you usually see like 4 blocks or something in a sort of paper. We have lots of little blocks. And then if you zoom in, you can see that there's this structure where those blocks are pretty dense. Now, this is just MATLAB graphics, so it's not very perfect. But you get the general idea that there's these dense blocks inside this big thing. And then the size of each block isn't that big. So as I said, you want d nodes of degree, d plus 1 nodes of degree d. At the higher end, of course, this is imperfect. But say your highest node is like degree 1,000, and your biggest block would be like 1,001 nodes. It's not very big. So we're going to compare the different methods that we talked about on a couple of small graphs, and then we'll show on some large graphs. So this is a co-authorship graph, and we have the degree distribution on the left. And we have the original data in red. Our method is blue triangles, and then we have stochastic Kronecker graphs in green and Chung-Lu in pink. And so they all do pretty well on the degree distribution. But where we see a real difference is with the clustering coefficient. So Chung-Lu and stochastic Kronecker graph have basically 0 triangles. And so their clustering coefficient numbers for all the degrees are really close to 0. And then BTER and Chung-Lu are in the same neighborhood. So it's not perfect. And we'll show more examples where it's not perfect, but it's closer than the others. So maybe we've learned something here about what's going on. And then here's another one, just a slightly different network. It has a lower overall clustering coefficient. And here also we see some of the oscillatory behavior of the stochastic Kronecker graphs. The green on the degree distribution is kind of going up and down. But the bigger story is on the right with the clustering coefficient by degree. The pink and the green are very low. They're far away from the real data. And the blue is a little bit closer. One interesting thing here is now we see that if we take the top 50 eigenvalues of the adjacency matrix, then BTER is a little bit closer than the adjacency matrices for these other 2 methods. And we can sort of think about why. So if you think about the number of triangles, you know that the number of triangles is equal to the cube of the eigenvalues divided by the sum of all of those divided by, I think, 6, if I'm remembering correctly. And so you have to get triangles right to get eigenvalues right, you would think. And so this gives some idea that if you get the triangles right, you get a little bit closer in terms of the eigenvalues. So that's really interesting, too, the role that these play, because we didn't optimize to the eigenvalues. So if we look at doing things in large scale, we can look at a graph. So this is a few years ago, back when 5 billion nodes was a lot. This was the largest graph we could find. It's called UK Union. And it's available at this laboratory for web algorithms in Italy. It has 122 million nodes, 4.7 billion edges, has an average degree of 76, and a clustering coefficient of 0.007. So we look over on the left, and we see the degree distribution produced by the real data and also produced by BTER. So there's a reasonable match, although we see that the UK Union has more variability towards the higher degree. And then we look at the clustering coefficient. So these are actually web pages. It's really interesting to me that there's this big drop-off around degree 500. All of a sudden, the clustering coefficient drops off. I assume this has something to do with like link spamming and trying to fool Google into giving things higher page rank or more priority in search results. And then apparently if you had 501 graphs in your promotion site, or 501 nodes, it was zeroed out in Google. And so they magically stop at like 499 or something. So we have this sharp drop off in the clustering coefficient. And then again, we see a pretty good close match between UK Union and the BTER. And we ran on a 32-node Hadoop cluster. Again, this was like, I think now 4 years ago. It took about 22 minutes on those 32 nodes. We see it is overestimating towards the higher degree, the clustering coefficient. It's one of those things that we should definitely fix at some point. But at least it's kind of getting in the neighborhood. The interesting thing here is the runtime for the model took 22 minutes. The counting of the triangles, just estimating it, took way longer. It took like 30 minutes. We wrote a whole paper about that. So I'll say more about that towards the end. But sometimes it's actually the hardest part is understanding what's in your data. And then the modeling maybe isn't so hard if you can just figure out your data. So the BTER model is sort of combining degree distribution and this clustering coefficient notion, which is measuring triangles. And then we're trying to also be scalable. So on Hadoop, we were running in 22 minutes on 32 nodes. But Hadoop is kind of slow. And actually, the version we were using back then was really slow. And so we also just tried it on an MPI cluster with 32 nodes. And then we could generate a bigger graph with 18 billion edges in 3 minutes. And that wasn't even sort of maybe, it was a good programmer, don't get me wrong, but we didn't really spend a lot of time making that efficient. So it's pretty easy to make this a very efficiently and scalable method. It comes close to real-world graphs. It matches the degree distribution for the most part. It matches the clustering coefficient for the most part. A lot of times the questions we get is, why do you pick those? And those are fair questions. We like to pick things that you can measure. And so you can have ideas about how the world works and try to impose those on your models. And we were trying to be agnostic and see what we could measure, and then if we could reproduce what we could measure. So you can ask yourself if that's interesting or not, but we thought that was interesting. The other thing is we can make a small parameter model. So right now, the input is you should take your real graph, get the degree distribution, which actually can be expensive to compute, get the triangles, which can be really expensive to compute, and feed that in. And a lot of people go, well, I don't want to give you that many parameters. That's too many. So we can satisfy even you. We can give you a 5-parameter version. And so you can tell us the number of nodes, the average degree that you want, the absolute maximum degree. That, if you're not sure what to do there, pick the number of nodes. You don't want a degree higher than the number of nodes. And Parallel, by the way, will like to give you more nodes than you have. The desired global clustering coefficient, and also some idea of the maximum clustering coefficient you would see. And then we can generate curves. We can do Parallel if you really like that. We actually tend to recommend the log normal instead. We think that's a better match for very large-scale graphs. But we still don't claim that anybody knows, including us, the right model for the degree distribution. But we find that's more realistic. So you give us those 5 parameters, can run a little MATLAB script. It'll generate a whole degree distribution and clustering coefficient profile, and then you can feed it into the model. So let's talk a little bit in the remaining time about bipartite networks. So many real-world graphs have this structure. We often kind of don't really pay too much attention to it. Examples could be things like author paper networks. In fact, when you do co-authorship, you're actually starting with an author paper network and turning it into a co-authorship network. User purchase history, user song playlists, actor movie connections, document keyword mappings. We heard talk today about Facebook. On my Facebook page, at least, there's a lot of discussion around certain news stories. You can imagine like users interacting with news stories and so on. So you don't always have same type of entities interacting. So you often have this bipartite structure. What a lot of people do, including me, is make product graphs. So just throw out the papers and just look at the co-authorship network, for example. But that discards information. I don't want to spend a lot of time on that. It's well covered in other papers. And in fact, 2 nice surveys are shown here. They sort of both have Latipi as a co-author. And these are really rich sources on bipartite graphs. So if we start thinking about modeling them, one thing you should notice is they have 2 degree distribution. So a bipartite graph, I should say what it is. So you have two partitions of the nodes. So in this picture here is sort of a blue nodes and gray nodes. And then you cannot have an edge between two nodes in the same partition, so two nodes of the same color. You can only go across. So you can have authors linked to papers, but you can't have authors linked to authors in the bipartite graph. And so you could just look at the degree distribution of the whole thing, but that would be kind of confusing. You actually really want to look at the degree distribution on the left nodes, the blue nodes, and the degree distribution on the right nodes, and treat those as two different things. So you have two degree distributions. And in fact, it's very simple to do sort of a Chung-Lu or configuration type model for this. Now, instead of having one bag of nodes that you randomly draw from, you have two bags. And you draw a red node based on its degree relative to the total number of edges, which is m. And you draw a right node relative to its degree over the total number of edges. And so you can still generate very nice graphs using this idea. And so let's just look at a simple example. Here is an author paper graph, 17,000 author, 22,000 papers, 59,000 edges. And then we have two degree distribution. So we have the authors on the left. And so the max degree of any author is around 100. And then we have papers on the right. And the max degree here for a single paper is close to 20. So you'd only have about 20 authors on a paper at most. But on the other hand, an author could have 100 papers. So they're sort of different in scale. So you don't want to just combine them arbitrarily. And then you can do this Chung-Lu procedure, and you can match it reasonably well. So when you have a bipartite graph, you can't have a triangle, right? Because you can't have a node on the same, two nodes connected on the same side. So what's the analog of that? So I don't know what people call it. We call it a butterfly. And that's Ali's kids that sort of came up with this naming scheme. So we have this idea. So it's also sometimes people call it a bow tie. And so those are the things that show cohesion. So it's two pairs of nodes that are fully connected. So fully connected subgraph on two pairs of nodes. And what can lead to a butterfly is these things called caterpillars. So we have three edges on these two pairs of nodes. And so we're interested in when caterpillars become butterflies, hence Ali's genius children coming up with this. So in the regular graph case, the clustering coefficient is 3 times the number of triangles divided by the number of wedges. And so for what we call metamorphosis coefficient, it's 4 times the number of butterflies divided by the number of caterpillars. And that's because there's 4 possible caterpillars for every butterfly, just as there are 3 possible wedges for every triangle. And that idea dates back to 2004 in Robbins and Alexander. I don't think they really had a name for it. And then we extended this because we like to look at more detailed numbers. So we did this per degree thing. But of course, it got really ugly and complicated. So we have this sort of multi-step definition. So you can define the metamorphosis coefficient for an edge to be the number of butterflies that involve that edge divided by the number of caterpillars that are centered at that edge. Okay, and so that means that that's the middle node. Somehow my Google voice thinks I'm talking to it. Stop. Okay, so you can do the metamorphosis per edge. Then the metamorphosis per vertex is just the mean of all the edges connected to a vertex, all their metamorphosis coefficients. And then the metamorphosis coefficient per degree is the average for all the nodes of the same degree. So it's kind of complicated, but you can get down to some numbers. And so if we look at just this global number, not by degree, we'll show some by degree later, the total number, 4 times the number of butterflies divided by the number of caterpillars, you get the metamorphosis coefficient. And here we have several graphs. Blue is the metamorphosis coefficient of the graph itself, and yellow is the Chung-Lu reproduction of that. And it's not very good, except for in the one case of movie lens that comes pretty close. And that's it's not a dense, I said dense graph, I'm kind of cheating, but there's a few movies that get a lot of the edges, and so that kind of produces most of the butterflies. It's like Star Wars 1, 2, and 3. Like you kind of watch all of them. But otherwise, it has a hard time reproducing this. And like you think I forgot some of the columns on like ConMat, but it's just 0. It doesn't even show up. So we can do a bipartite version of BTER called biBTER. And so it gets a lot more complicated, because now it just takes some nodes from the left and some nodes from the right, And they each have different metamorphosis coefficients, even if they're all the same degree on the left, and then another same degree on the right. And so to figure out how to match those up, figure out how many to get, so this whole complicated math that we do. And it's a miracle that it works at all, I have to say. But we generate these, and then we generate our affinity, our sort of Erdős-Rényi, but bipartite Erdős-Rényi graphs that give us our butterflies. And then in phase 2, we just connect everything else up to get the right clustering coefficients. And so again, there's this structure that, and this is from a real graph, before it was from a fake parallel graph. We have a bunch of nodes of degree 1. Those sort of aren't in any block. And then we have these bunch of little teeny affinity blocks. And we zoom in, and they're still small, but they're rectangular, and they're funny shaped. But they're sort of dense, and that's the key. And the rest of the graph is sparse. But I'm not going to really go into how we construct that. But now you can see we generally do better. So yellow is the biBTER model. And movie lens are actually overestimating. So see, sometimes we're still wrong. So I'm not really going to tell you how to model graphs correctly, just a little more correctly than before, and only in some cases. But we're able to get something that's a little bit more realistic for the rest of the graphs. And just to give you some look-sees at this is that ConMat author paper thing. We showed before the degree distribution. That's on the top. On the bottom, where most of you can't see, is the butterfly business, the metamorphosis coefficient by degree. And so the orange is Chung-Lu because it doesn't make butterflies. And then the blue is the real data, and the green is ours. And so it's in the neighborhood. I'm going to do sort of binned ones for the rest because some of them just have too many points to see. So that's the same data you just saw in a binned version. And so here we go up to 1.5 million edges. So we see that we have a better match. We go up to 8.5 million edges. These are interesting because they have funny-looking metamorphosis coefficients where they're high for a while, and then they drop off around 200 on the left and 1,000 on the right. This one's interesting because of the data collection. They didn't collect any critics unless they reviewed at least 10 movies. So you have this sort of missing data problem, which you're just like, well, that's funny. And so the models predict some nodes of low degree. And then here's a song one where they didn't do any users on the left this time. They didn't do any users that listened to less than 10 songs. And so we can see this. It's sort of nice that we can get somewhere in the neighborhood of having the right butterflies. We're clearly a long ways off from having exactly the right numbers. It's a topic for future study. But I think we've sort of uncovered something that gives us some idea of what's really going on. Here's 56 million edges. And this is all in like MATLAB. So we can, not that these are really big graphs, but it's pretty fast to generate these types of models. And here, oh, here's 112 million. So you kind of get the basic idea. So what we're really going after in modeling graphs is, at least for me, from a mathematics point of view, is understanding what we can actually model. I feel like we hear a lot of like, we tried this, we tried that, and that sort of looked more like what we saw, but we don't really know why. And so we want to know, well, why might it look more like what you're seeing? What are fundamental properties? What are the physics of social interactions, if there is such a thing? So we have these BTER and biBTER graph models. So we're identifying that we need either triangles or butterflies, and that we have to have these dense subgraphs to make that happen. It matches the degree distribution and clustering coefficient. We have scalable Hadoop and MPI versions. We have a reference MATLAB code that you can download. We have this way that you can generate fake graphs using our just 5 parameters. I haven't talked about it at all, but counting triangles and butterflies is the most expensive part. And actually, Pinar has done a lot to make this possible. And I've just sort of been annoyed by this. Like, triangles ended up to be this massive sort of sideline that we talked about how to sample, to estimate the number of triangles. And that was a whole line of work they haven't given the citations of here. And there's still a lot to do. So I haven't talked at all about network evolution. I even had a grant to do network evolution. I never really got to it. What do you even measure? I don't even know how to measure like things changing in time in some way that everyone can sort of see is obviously the right way. Overlapping affinity blocks, we haven't done that. But clearly, if you think about social networks, that's happening, or biological networks. Hierarchical affinity blocks, there's a lot of interest in hierarchy. It seems like an obvious extension. And then, as I said, counting everything is a lot of work, and often the hardest part of doing all this. And I think why people didn't worry about it so much earlier on. It's like, gee, it'd be nice if we could match the triangles, but gosh, we can't even count them. So, oh well, that would be next year, we'll worry about that. So references on the right, and I'll stop here. Thank you.